So as we said at the end of the last video, the process of logarithmic differentiation really wasn't necessary in example number 3. It was possible to be used, but it almost seemed like it overcomplicated the question. But this doesn't mean that logarithmic differentiation in general is always a waste of time. In fact, there are very specific instances when logarithmic differentiation must be used because we have no other tool by which to help answer certain questions. And such a question here is example 4. How would I find the first derivative of a function like y equals x to the x? And I'm assuming here that x is a value greater than 0. Well, I could recognize right away that I can't use the power rule here because the power rule required, again, that I had something like x to a number, and I don't have that. I can't use a rule like a derivative for b to the x because that required number to an x. So for something like this, I used the power rule. For something like this, I used exponential derivative rules. And I'm going to go ahead and actually write down this kind of quick summary over here on the side. So for something like x to the n, we know that we used the power rule. For something like b to the x, I'll say we use the exponential rule. And if I had something like, let's say, number to a number, well, that's really just a number. So for that, I can use a constant rule, right? That is, the derivative of number to a number would just be 0. But it's in exactly the moment when I have x to the x, or something with x in the base and something with x in the power, it's exactly in this moment where I must use logarithmic differentiation. So this right here is a really helpful summary. It tells me exactly when logarithmic differentiation must be implemented. When I have something with x's in it raised to a power with more x's in it. So let's take a look here at something like example 4 to see how I would actually use this here. So I'm going to start by taking the logarithm of both sides. So I'll say we take the natural log of both sides, and then we will use implicit differentiation. So let's see. If I have y equals x to the x, that of course is going to mean that the natural log of y is equal to the natural log of x to the x. Now, why is it so important here that I use these natural logs? Because I'm like, if I try to just take the derivative implicitly right now, I'm still going to need to figure out how I do the derivative of x to the x. But notice that if I make use right now of logarithm properties, I can actually, that was a terrible arrow, I can actually go ahead and rewrite that other side by using the power rule. And I can take that value of x and bring it down to the front, and now I have x times natural log of x. So now that I have this, I can go ahead and I'll take the derivative of both sides, because instead of having now x to the x, which is very complicated to work with, I have x times a natural log of x, which can be tackled with just a simple product rule. And so let's go ahead and take our derivative here. Derivative of natural log of y is going to be 1 over y dy dx. Over here I'll do the product rule. And so I'll write this as 1 times the natural log of x plus x times 1 over x. If I try to get dy dx by itself, I'll have to multiply the value of y over onto the other side. So I'm going to get y times, this looks like it's going to be natural log of x plus 1. So I almost here have a final answer, and I'll just write down the last little bit here as dy dx is equal to, and again I can replace y with x to the power of x. So what's the derivative of x to the x? Well, it's x to the x natural log of x plus 1. This is actually one of my favorite derivatives. And I would actually ask you to go, like, if you know anybody who's taken Calculus 1 before, go actually ask them how they would calculate the derivative of x to the x. And chances are they will not remember that this is something that they need to do with implicit differentiation, because oftentimes in a lot of classes this doesn't really get emphasized, or it's not very clear to students when exactly they need to use it. So one big takeaway here is to notice that whenever I have something like x to a power of x, or something with x to another power with x, logarithmic differentiation is important. So that includes all sorts of different examples. This could be something like if I wanted to take the derivative of, I don't know, how about x to the sine of x? I need logarithmic differentiation. If I wanted to do something like x squared plus 1 raised to the power of x squared, I need logarithmic differentiation. Anything where there's an x in the base and an x in the power, I need this particular approach.